Hi everyone. I'm recording this to make up for the week we missed. The first recording here, I'm going to break this up into a couple of different recordings. The first recording here is going to be just talking about what we did last week, or I should say the week before, because we missed last week because I was sick. So the week before last, right, we did the repeated measures ANOVA, and we also did post-hoc tests, right? But we did the post-hoc tests for the regular independent samples ANOVA. In this recording, what we're going to do is we're going to do the same post-hoc tests, but for repeated measures ANOVA. And by doing that, that's going to, you know, it's going to be very similar, right? I said last week, it's very, very similar. We're just changing a couple of things. It's almost no different, right? And so then in the second recording, I'm going to do some two-factor ANOVA stuff, which is the new stuff. And then I'll make a third recording with SPSS. So those will be our three recordings. It might be actually a little bit longer than a full class in the end, or it might be shorter. I'm not sure yet. It's hard to say. Let's just see. All right, so we had this example. I think I used the same example last time, right? But this is repeated measures ANOVA. If it's not, maybe it's not the same example. These numbers are not that familiar to me, actually. So yeah, I'm thinking this is a new example. Right, this was the tutorial slides from the previous week, which I did not. So this is a different example than the one that we did, right? So we have 3 different treatments, and we have 5 different individuals, right? And for each treatment, we want to calculate the total and the mean and the sum of squares, right? And the way I do it, I also like to calculate the sum of the x squared for each of these columns. So let me just draw that in here, right? So we've got, first we've got 26 squared, and then 30 squared, and so on. Right, so we have 676, and then 900, and then 529, and then 784, and then 841, right? And you have to do this anyway, even if you're using the other method, because you need to get the total of all the squares anyway. So might as well just get that all done, right? So now we're going to do 27 squared is 729. 31 squared is 961. 25 squared is 625. 28 squared is 784. 29 squared is 841. Over here we have 900. 1225. 27 squared is 729, so we have that again and again. And then 31 squared is 961. And so if we add these up for each column, I'm getting 3730 for the first column, right? And I'm not going to leave a lot of pauses in here, so it's a video. You can pause it yourself, right? Normally I would leave pauses for questions and stuff, but I'm just going to kind of go straight through. Pause whenever you need time to process what I'm saying or catch up or whatever. All right, so I'm just adding up the squares, 3940, and then 45, 44. And if I add these 3 up, I should get the same thing, I hope, right? If I've done everything correctly. I do. I just did it on my calculator, and I do indeed get that. Right? And when I add up these columns, I get these totals here. Right? The individual columns, I just add them up. And when I have those totals, I get the grand total there. Right? So this is all checking out. This is all working. Right? Then what I want to do, right, is I'm interested in getting the sum of squares within the sum of squares, and I'm going to split that. Right? I'm going to get the sum of squares within, which I'm going to split into the sum of squares between subjects and the sum of squares error. And then I'm also going to get the sum of squares between, right? And the sum of squares total. Right? These are all the things I'm going to get. Right? So for each of these categories, I'm going to do my usual formula, right? I'm going to do my usual formula. Remember, the sum of x squared minus the sum of x squared over n, right? That's my usual formula. So I'm doing, in the first case, I'm doing 3730 minus 136 squared over 5. And I get 30.8, right? That is what I get. And then I do the same thing here, 3940 minus 140 squared over 5, and I get 20. And then I do 4544 minus 150 squared over 5, and I get 44. So my sum of squares within, I get just by adding those together, right? This and this and this. Put those together, my sum of squares within 44, 64, 94.8. 94.8, which has to be split into two pieces later, but for now that's fine. Right? And I can do the total. I can do the total by doing the 12,214 minus 426 squared over the grand total of n, right? The 15. Right? And that gives me my SST. So 12,214 minus 426 squared over 15 gets me 115.6. Right? That's my SST. And then my SSB, my between, is going to be just subtracting, right? I just have to do the 150. Let me not do that right there, just because I want some space there for that. But I'm going to do the 115.6 minus the 94.8, and that's going to get me 20.8. Right? So now I have my SS between, my SS within, my SS total, and what's left is to split the SSW into the SS between subjects and the SS error, right? Remember, the SS between subjects is how we were going to do that, right? So for that one, if you remember, there were a couple of ways to do it. The way I like to do it was to square each of these, right? So 83 squared, I'm getting 6889, and then 96 squared, I'm getting 9216. And then 75 squared, I'm getting 56. Hold on, let me just erase that circle. It's getting in my way here. Right, I'm getting 56.25. And then 83 squared again is 68.89 again. And then 89 squared is 79.21. Right, so I add all those up. I'm getting 36,540. And when I add all these up, I get the 426 again, right? Because this is the same as the grand total here for this column, right? So now I'm going to switch to a different color here. I'm going to use, let's say, blue. I haven't used blue yet, right? What am I going to do? I'm going to do my same formula again. I'm going to do the 36,540 minus the 426 squared over 5. But then I'm going to have to do the whole thing over 3, I think is what I said last time. And that's going to get me 81.6. And that's my 81.6 here. Okay, so use the same formula, you divide by 3. Why are we dividing by 3? That's the number of treatments. Right, and going through these notes, you'll see there's a slightly different formula you can use to get the same answer here. And it's totally fine. Whichever method you want to use, whichever formula you want to use is good. It gets you all to the same place, right? I'm using this method. This is the one I like because it's just the same formula over and over, which I find easy. All right, so that's one more number we need, the SSE, the error, which I will use, I guess, orange for. So I'm just gonna say, well, this has got to be the 94.8 minus the 81.6, right? Right, so 94.8 minus 81.6 gets me 13.2, and that's a little bit hard to see. This orange is quite light. Maybe I'll pick a slightly different. Can I pick a darker orange? Yeah, this is more of a brownie orange, but that's fine. 13.2, right? 94.8 minus 81.6 gets me that 13.2, right? Because these two numbers have to add up to the green number. Okay, so there we go, right? And then we can put that in a table, right? And here are all those, calculations again. Right? But when we do this all, we put it in a table. Oh, actually the table's not here in the notes. That's okay. We can draw off the table, right? Now we have all of these. All right, let's just draw a little table down here where there's some space, right? So we're gonna have the SS, the DF, the MS, and the F. And we have, right, we have the between subjects, the error, and the total, right? So we had 20.8, 81.6, 13.2, and 115.6. And then the degrees of freedom, right, for the total is capital N minus 1, right? Capital N minus 1, which is going to be 14. And then the between groups, between treatments, that's the K minus 1. So 3 minus 1 is 2, right? And then these ones, right, the between subjects should be 5 minus 1, which is 4. And then this should be 8 because it all has to add up to 14, right? 2 plus 4 plus 8 equals 14. So that one makes them add up, right? Here we had the K minus 1, and here we had the number of subjects minus 1, right? Which was little n minus 1. Right, and then we just do some division for each of these, right? We don't need to do that for the total, but we can do it for each of these, right? 20.8 divided by 2 is 10.4. 81.6 divided by 4, we don't need to do. We could do, but we don't need to do. 13.2 divided by 8 is going to be 1.65. Right, we don't need to do this one. We don't need to do that one. And then 10.4 over 1.65 gets me 6.30. And that was my test statistic. All right, and having all this done is going to be, this is a recap. We're doing the stuff that we've already done, but you'll see when we do the post-hoc tests, right, you need to have this done in order to do the post-hoc tests. All right, so, and we'll see that this should match up with all the calculations that are here on these pages, right? When they get the 10.4 and the 1.65 and the 6.3, that matches up perfectly with what we had, right? And then we need to compare that test statistic to a critical value, and the critical value should have the degrees of freedom, which are the 2 and the 8, right? The numerator and the denominator, 2 and 8. Right, so when we go to our F table, there's an F table here somewhere. I thought there was. No, maybe not. There's the Q table here. So I saw the Q table when I was looking through. Oh no, here's the F table. Here it is. Right. F table. So we have like the 2 and the 8. Right. So these are the numbers we're looking at depending on our alpha. If we're using alpha is 5%, then we're doing 4.46, and we have a significant difference. If alpha was 1%, we would do the 8.65, and we would not have a significant difference because our 6.3, the F statistic, was less than 8.65, right? So at 5%, we reject the null hypothesis. At 1% alpha, we do not reject. Right, so whether we reject the null hypothesis depends on what our alpha was in this case. Right, so if it was 1%, we didn't reject alpha, there would be no follow-ups. We did not find a significant difference between any of the groups. Right, so we don't need to go ahead and check which differences are significant, because the answer is going to be none of them. None of them will be significant at 1%. Right, but at 5%, then here we need to do follow-ups, right? So here we are done. Whereas here we need post-hoc tests. Okay, so let's assume we're in this 5% situation, right? We're doing alpha equals 0.05, alpha equals 5%, and we're going to reject the null hypothesis, so we're going to use post-hoc tests. How would we do that? I'm going to show you how we do that using Tukey and using Sse, right, for repeated measures. So if we go down here and we see, right, this is the formula we used last time we did Tukey, but I told you all you have to change is change MS within to MS error and change the degrees of freedom you're using. Right? So the old way would have been to use the MS within and then use the degrees of freedom within, right? But here we're going to use the MS error and we're going to use the degrees of freedom for error. Right? The degrees of freedom for error we have, if we look up, that was 8. Right? If you don't remember that, we can scroll back up to our table here. 8, right? That was the degrees of freedom for error. And that'll get us Q, right? So Q equals, right? So here the number of treatments is 3, and the degrees of freedom for error was 8. So we are looking at 4.04 because we're doing alpha equals 0.05, right? That's why we're not looking at the bold one, because we're doing 0.05. Right, so we have the Q equals 4.04, the MS error and the N we have, right? The N is 5, and the MSE is, if we don't remember, we can go back to our table and see what that was. That was the 1.65. All right, but you can see that right here, MSE, 1.65. Right, so then my HSD is going to be 4.04 times the square root of 1.65 over 5. And I can plug that in my calculator. And I get 2.32. That's my HSD, my honestly significant difference. So what do I do with that? Well, with that, now I go back to my means, my group means, and I see which ones were different by more than this amount. All right, so 2.32. All right, if we go back to our group means, here they are. Let me do this in, I don't know, I'll do it in this dark red here, right? So I'm doing my group means, and I'm doing the HSD equals 2.32, right? So between this pair, the difference is 0.8, right? 28 minus 27.2, that is significant. Between this pair, the difference is 2, that is significant. And then finally, between the third pair, the difference is 2.8, which is not significant. Sorry, other way around. I'm saying significant. I meant not significant. Sorry. The 0.8 is not significant. Yeah, sorry about that. The things I said were significant were not, and the one I said was not significant was. I just wrote it backwards. Right? The 0.8 is not significant. The 2 is not significant. The 2.8, that is significant, right? So we do not have a significant difference between group 0 and group 1. We do not have a significant difference between 0 and 2, but we do have a significant difference between 0 and 2. Right? So that's the result from our Tukey test. Right? Is that mean 0 is not equal to mean 2. Based on Tukey. All right. The other ones, we cannot reject the null hypothesis, right? The null hypothesis is that they're equal. And so in those cases, we don't have enough evidence to reject, right? Mean 0 might be equal to mean 1. Mean 1 might be equal to mean 2. We don't have enough evidence to reject, but we do know that 0 is not equal to 2. Okay, so that's Tukey. And now we're going to do Sse. Right, so with Sse, right, if we go back down here, right, with Sse, we're just going to do we're going to change the numerator to an MS between calculated using only the two treatments that we are comparing with the same denominator as before, right? So this is what we had already. This is our table we already had. And what we're going to do is we're going to say, okay, well, what if we change this and that, and then therefore that? Would it still be significant? And remember, the critical value is 4.46. Right? So that's going to stay the critical value. .46 was the critical value. Okay, so now we're going to do 0 versus 1. We're going to do 0 versus 2. And we're going to do 1 versus 2. And so for this, right, we need to calculate a new between treatments variance. All right, and then the between treatments variance, we're going to use for each of these, we're going to use the sum of t squared over n minus g squared over capital N for each. This is going to be my SSB for each of these, right? So we need to know what are the group totals. That's the most important thing, is the group totals, right? So if we go back to here, the group totals were 136, 140, and 150. 136, 140, 150. With those, we should be able to sort this out. Oops, I've gone too far. Way too far. All right. So for 0, I had 136, I had 140, and I had 150. All right, those were my group totals up here. 136, 140, 150. Okay, so for 0 versus 1, the grand total is going to be the 136 plus 140, which is 176. And the n is going to be 10 because it's 5 plus 5. There were 5 in each group. So when we do this formula, we're going to get 136 squared over 5 plus 140 squared over 5 minus, that should be 276, sorry, 276 squared over 10. Okay, and so then we're going to get, let me plug that in my calculator, 136 squared over 5 plus 140 squared over 5 minus 276 squared over 10, and I'm getting 1.6. So obviously this is very small. And when I find the MS between, that's going to be 1.6 over 2 is 0.8. And then the F is going to be 0.8 over 1.65, which is going to be some small number. .485, which is not significant, right? So there's no significant difference between 0 and 1, which is what we got with Tukey, right? So this agrees with the Tukey test so far. Right, when we do 0 versus 2, we do the same thing. Actually, I'm going to just change colors just to have different colors going on, right? 0 versus 2, right? So we're going to get the grand total by adding these together, 0 and 2, 136 and 150 is equal to 286, and the n is still 10. So then my SSB is going to be 136 squared over 5 plus 150 squared over 5 minus 286 squared over 10. And that's going to give me 19.6. And then my MSB is going to be the 19.6 over 2, which is going to be 9.8. And then my F is going to be 9.8 over 1.65, which is going to be 5.93 or 5.939, right? Which is greater than 4.46. So this is a significant difference, right? 0 versus 2 is significant. And that's what Tukey said as well, right? Tukey said that 0 versus 2 was the only significant one, right? And so we're actually probably going to see the same result with Sse, right? It's very common for Tukey and Sse to agree because they're testing the same thing in two slightly different ways, right? They don't always agree because they are different methods, but they frequently do. All right, now if we do 1 versus 2, Tukey said this was not significant, so we're expecting to see that this is not significant. That's what we're expecting to see, right? So we've got the grand total is the 140 plus the 150 is equal to the 290. So then the SSB is the 140 squared over 5 plus the 150 squared over 5 minus the 290 squared over 10. And that's going to be 10. And then my MSB is going to be 10 over 2, which is 5. And then my F is going to be 5 over 1.65, which is going to be 3.03, which is not significant, right? So like I said, we expected this to agree with the Tukey, and it did, right? 0 versus 1 is not a significant difference. 1 versus 2 is not a significant difference, but 0 versus 2 is a significant difference. Okay, and so the Sse test agrees with the Tukey test about which treatment groups had significant differences. It was only the 0 versus 2. Okay, so that's how those post-hoc tests look when you have a repeated measures test. And they're almost the same as what we did before, right? They're almost the same as the independent measures version, right? Very little in terms of how they were different. Right? The Sse test especially is exactly the same. The only thing is, like, in the other version, we would have had a within here that we were using as a denominator instead of an error term we were using as a denominator. Right? That's the only difference. Right? We would still be doing the same thing where we do this, find the grand total, find the SSB and the MSB, divide by the old DF, get the new F, right? It would be the same thing. Right? And then the Tukey, the only difference in the Tukey is MS within becomes MS error, DF within becomes DF error when we're looking up Q. Okay, so that's it. And that becomes the end of this part of the recording because the next thing is two-factor ANOVA. So I'll stop this here, and you can watch the next video for the next part.